transpetaflopsных initiative, but currently, for us, the transpetaflops is just now for us, rather than the future technologies. So then I'd like to introduce just the K Computer. And just yesterday, we had the HPC workshop. So at that workshop, I also talked about the introduction of the K Computer itself. So most of my slides overlapped with the materials at HPC Asia. But in addition to the introduction of the K system itself, but also when we consider about the transpeter initiative, also we should consider about the facility for the systems. So I'd like to introduce the facilities for the K computer systems. So again, I should mention about our nickname K. K means the 10 to the 16th power in Japanese numerics. So our performance target is 10 petaflops. Yesterday, we got the #1 performance in NIMPAC. Just that is our current the system under development. So our final target is 10 petaflops. And K also means in old Chinese character arch. It's to a new era of computational science. So here shows the schedule of the project. The project itself started in fiscal year of 2006. In 2006, our Japanese government made a plan for third science basic policy for science and technology. So in that plan, the high-performance computing technology was designated as one of the key technology of national importance. So then our government started the project of the development project called the next generation supercomputer research and development. So about 1 year, we made a so-called what we call the conceptual design. And after the detailed design, we had the prototype chip, and then now the installation phase. And the hardware itself is almost completing, but currently most work is being done for the system software development. Our project developed everything from the scratch, including hardware and software. So in this project, also the government invested fund for the development of the application focused on the nanoscience and life science area. And also we constructed a new building for the computational center in Japan. The facility itself is completed last May. So our office was at that time in Tokyo, but our team, development team, was moved to Kobe after completion of the building. Okay. So the K Computer will be served as a national leadership infrastructure for science and technology development. So in that sense, the application area is not limited to the specific areas. Our computing center is a general purpose to serve for all the scientists and engineers in Japan. So those are the major applications on the K computer. It's not limited to some specific, but in this project, the government funded to the nanotechnology and life science area. But after the completion, from the basic science to the engineering or manufacturing area is also used for this computer systems. And also the government selected what they called 5 strategic field application areas, mainly the major users of these K computers. The first area is the life science areas, and second is new material energy, new material development and new energy development like solar cell, the efficient solar cells or biomass energy. Those are included here in these application areas. And the third one is the environmental areas like global climate change prediction for disaster prevention and mitigation, including the earthquake simulation also. And fourth area is monozukuri. It's engineering or manufacturing areas like crash areas or engine development or some fluid dynamics areas. Those are the included here in this manufacturing or engineering technologies. And fifth area is the so-called basic science areas from particle or physics to astronomy. So these are the some project leader in these areas. So as I mentioned, that this system served as this national leadership systems for science and technology areas, not limited to specific areas. So then, around when the project started in 2006, we set the design targets, several design targets. One is the 10 petaflops in Nepal. And second is the petaflop sustained performance in real applications. Impact number is just only one measure, but from application users' viewpoints, sustained performance is a key for those users. So then our target is to realize petaflops performance in real applications. And the application is not limited in some specific areas, so then we have to support a broad range of applications for computational science and engineering. And also the simulation results will become very huge, so then we support a huge amount of data storage, and also we have to handle efficiently for I/O data access. And also, this is a very huge system, so then power consumption is one of the key technology areas to reduce the powers. And the final one is a highly reliable system. So we need many parts, many chips. So then, and also this system must serve as a national infrastructure. So then system must be highly reliable systems. So to realize these design targets, so application, particularly application is not specific areas. So then we try to realize these design targets by general purpose processor, and also keeping the conventional programming and operation environments, and not some peculiar environment, but the general purpose compatible development environments we targeted at. And also in 2006, the project itself is the development project from the scratch. So then our application committee selected 21 target applications for system development and system evaluation purposes from the area of nanoscience, life science, engineering areas, or some basic science areas. And so those 21 applications include typical numerical scheme like molecular orbital calculation, molecular dynamics, or FFT, or some finite element method or fluid dynamics, and those typical numerical scheme are included in those 21 target applications. But frankly speaking, that the 21 evaluation target applications are too many. So actually, we selected 6 applications of these 21 applications. Currently, the typical 6 applications are ported on the K computer and the tuning. Actually, we now focus on the 6 applications of the 21 target applications now. And at the 2006, we also surveyed around more than 20 or 30 computer center of universities or national institute. And we had requirements for the future systems. And major their problem is the power problem. So then we set some target power consumption maximally at 30 megawatts, including everything, the facility and also. So then current our upper limit of the power electricity capacity is 30 megawatts, but the system itself is very low than 30 megawatts. In this RIMPAC 8 petaflops, we achieved around 10 megawatts or so. Okay? So then at a normal running environment, 50 megawatts or so is computer systems power consumption, I think. And reliability, operability is also their requirements from a computer center. And also we surveyed various technologies. Particularly, we selected as a basic semiconductor technology the 45 nanosecond, 40 nano process technology. At that time, the 90 nano process is the major process technology at that time. So then we selected 2 generations ahead for the development of these systems. Next is system volume. So finally, the current systems, our developed system is a massive parallel systems, not to use any specific accelerators, nor some application-specific accelerators. Just the general purpose processor we developed based on the Spark architectures. So to realize sustained petaflop system in real applications, the CPU itself is high performance, low power with 8 cores. The peak speed is 128 gigaflops at 2 gigahertz, and it's very low power, 58 watts. So gigaflops per watt is one of the highest, one of the lowest power per flops. And also this is a massive parallel system, so then network is one of the key areas for development. We employ the so-called TOF network. It's a torus, logical torus networks. And also we developing the optimized compilers and libraries tuned for these systems. And the system itself must be a highly reliable system. So then our chip employ the low operating temperature mode. Usually the PC chip, operating temperature is around 80 to 90 degrees in centigrade. But it's by lowering the operating temperature, we can improve much more reliabilities. So to reduce the operating temperature, we employ water cooling systems. And next important one is for highly reliable system is the auto recovery functions with the error detections. So recently that they say the more the chip parts, we will face the more the what we call the so-called intermittent failures or soft errors or spontaneous errors by radiation or some fluctuation of the power or fluctuation of the clock. It may cause some spontaneous or soft errors, not a solid error. It's an intermittent error. So we need a very strict error detection. Error detection in this environment, error detection is very important. And once error detected, it's an auto recovery function also important. So inside CPU, we have these kind of reliability functions. And network itself must be reliable. And also, as a system, there are some backup servers and data paths in IO. And also, the system must support the efficient usable system for diverse workloads. So, particularly in the IO is a very important area. So then we employ the distributed parallel file system based on the rasters. And also, one of the features of IO system is that we employ the so-called staging functions, hierarchical IO systems. And also we are developing now efficient job schedule to support the 3D torus network. Okay. So here shows the system configuration. The central part is compute node. There are more than 80,000 CPUs, and one CPU has 8 cores, so then there are 640K cores, and total memory capacity more than 1 petabyte. So here is the local file system dedicated to the compute nodes. The capacity is around 11 petabytes, and we have the global file system, more than 30 petabytes of the global file system. It's sharing. It's a common data files are stored here. In addition to the main body, we have several management servers and login front-end servers. This is computer nodes. One computer node has physically 10 connections. This is the physically 6-dimension networks, but the logically 3-dimension torus networks. So and also there are several redundant paths. So then once some error happens, automatically the path is rerouted to maintain the systems, not to shut down the systems. Here so the chips. Architecture, chip architecture is 8 cores and shared 6 megabyte second cache, and clocked at 2 gigahertz. And process is Fujitsu's 45 nanometer CMOS technology. The chip size is more than 2 centimeters by 2 centimeters. And performance 120. And it has a very high speed memory band, 64 gigabytes. And power is 58 watts by water cooling is supported. So by reducing the temperature, we can have a low leakage current that leads to the low power and high reliability. Here shows how the basic performance CPU. It's a basic CPU, 3 barrier synchronization, the CPU supports the barrier synchronization for intercores for the vectorization of the inner do loops, like vector processors. The very short barrier synchron by supporting the very short barrier synchronization of 49 nanoseconds. And network chip has a throughput between the two nodes, peak the 5 gigabytes. And also, I should say about the current configuration of the DIMPAC, more than 8 petaflops in efficiency of 93%, and cores at more than 500,000. It took about 28 hours. There's no failure in this 28 hours. And we watched the power meters. So the 4 to 5 megawatts, between the 4 to 5 megawatts, the fluctuates power. The peak is around 9 megawatts or 10 megawatts, but some stable situations, let's see, 4, 5, or 6 megawatts, but in the peak, so that width of power is 4 to 5 megawatts in limbo measurement. Yes, this software based on the Linux operating system, we supporting several job management or system operation management softwares like a job scheduler or job monitoring or the user support or something. Those kind of newly developed. And also the file system based on the rasters and compilers, the libraries, and also the debugger or profilers or such kind of performance tuning tools also being developed. Here shows the Linux. This is the image of the K computer. Here shows the installation started in last October, and this is the computer room is on the third level of the computer building. And one of the features is no pillars to have the flexible layout, and also to reduce the wiring problems. And there's no, and the cabinet weight of the cabinet is around 1 to 1.5 tons. So then only the computer system is more than 1,000 tons to support these very heavy racks without pillars. That is very sophisticated buildings. Next, the applications. Currently, limited users started to use a part of the K computer as a trials for the system evaluation and performance tuning since this April. So here shows the distribution of the current application, life science, material and energy and environment, and the industry applications, fundamental science. So these are the typical applications: a global circulation model, it's a climate, and molecular dynamics, and density function theory for material design, and fluid dynamics, and seismics, and particle physics. So one of the example of the seismic is shown here. This is the reproduction of the earthquake and tsunami on March the 11th. It's a coupled model of the ground motion and tsunami. And this simulation itself executed on the Earth simulator. It took about 2 hours, resolution 1 kilometer. But even if that the resolution is reduced to 0.25, 1/4, on the K computer, it would take only less than 10 minutes. So it suggests that this is a reproduction of the tsunami, but immediately after the earthquake occurred, on the K computer, we may have a possibility to make a real-time simulation before the tsunami reaching the coast. Next, finally, I'd like to show some facility for this system. This center is located in Kobe on the artificial island just next to the Kobe airport. Yes. This is the artificial island, just around 450 kilometers west to Tokyo. So here's the layout. So this is the research buildings, and this is the computer building. So these are the water cooling chillers, and this is power supply buildings. This is after the facility. So the third floor we have the computer itself, and the ground floor we have global file systems. To connect these, we have so-called optical fiber. Through the optical fiber connected to the global file system and computer systems. And in between we have air handling unit room. System itself is a mixture of water cooling and air cooling. So air is circulated like this, and water is circulated through the heat exchangers. Here shows the features of facilities. One important one is the preparation for the earthquake. So before the construction of the building, we made the soil improvement for prevention from the liquefaction, liquidation. Okay. And building itself is an isolated structure by dampers. There are several dampers, rubber damper, or lead damper, or steel dampers. And as I mentioned,